Hi and welcome to part 5 of my video playlist about the preparation of arylamines. This video is about the amination of arenes by substitution of hydrogen. I'll show you examples of both electrophilic and nucleophilic aminations, but no photochemical or electrochemical transformations. These usually require special equipment and are difficult to scale up. Electrophilic nitrations are discussed separately in part 6. A number of electrophilic reagents can generate a carbon-nitrogen bond upon reaction with electron-rich arenes under acidic conditions. These include hydroxylamine derivatives and halogenated amines or amides. If a given arene isn't nucleophilic enough, metallation can yield a more reactive intermediate, better suited for electrophilic aminations. Then, several electrophilic reagents will form carbon-nitrogen bonds with electron-rich arenes, but without yielding an arylamine directly. These include azo compounds, diazonium salts, nitronium salts, nitroso and nitro compounds. The products can then be reduced to arylamines. Electron-deficient arenes can sometimes be aminated with an amine and an oxidant. The tricky part is to find oxidants that will not react with the amine directly, but only with the addition product of the amine and the arene. Alternatively, if one of the R groups of the amine sketched here is a leaving group, then no oxidant would be required for nucleophilic amination. Thus, hydroxylamines can, for instance, aminate electron-deficient arenes directly. Also, nitrogen-centered radicals can add to arenes and yield arylamines. Nucleophilic aminations in the presence of oxidants sometimes also proceed by a radical mechanism, in particular with amides or imides as aminating reagents. Let's have a look at some specific examples. Here, hydroxylamine was activated with titanium trichloride in the presence of terz-butylbenzene. As expected, a mixture of isomers resulted in this instance. Methylated hydroxylamine is also a suitable electrophilic aminating reagent. In this example, anisole was converted into a mixture of 3 isomeric methoxyanilenes by treatment with methylated hydroxylamine and catalytic amounts of iron sulfate. Brominated aryl ethers were more resistant to this type of amination than simple phenyl ethers, as shown here. Only the phenoxy group reacted, but again, a mixture of 2 isomers resulted. Also, anilenes seem to be resistant to this amination strategy because, despite the excess of electrophile, no twofold amination occurred. If the starting material can form chelate complexes, unexpected regioselectivities can result. In this example, a benzyl picolinate only yielded the meta-aminobenzyl ester when treated with an activated hydroxylamine and catalytic iron. Instead of activated hydroxylamine derivatives, also mixtures of amino group containing compounds and oxidants can serve as electrophilic aminating reagents. The amino group containing compound must of course be sufficiently resistant to oxidation. Here, 3-aminopyridine was activated by diacetoxyiodobenzene. The reactive intermediate probably contained a nitrogen-iodine bond. This example is closely related to the previous one. Here, a substoichiometric amount of aryl iodide was oxidized with peracetic acid and used to activate a protected hydroside. Unfortunately, a large excess of arene was required to trap the activated hydroside. Sodium acide in combination with acids can also bring about the amination of electron-rich arenes. In this example, paraxylene was aminated with just one equivalent of sodium acide and a large excess of boron trifluoride etherate. Electrophilic aminations are often conducted with azo compounds as electrophiles. Azo dicarboxylates are particularly reactive and yield protected aryl hydrazine derivatives, as in this example. The amination was catalyzed by gold chloride, but other acids should also do the job. I'll show you now some examples of electrophilic aminations under neutral or alkaline conditions. In this example, phenyl magnesium bromide was treated with benzoylated N-hydroxymorpholine in the presence of catalytic copper and zinc chloride. The electrophile was prepared from morpholine and benzoyl peroxide. Polyhalogenated arenes can be sufficiently acidic to enable metallation by alkoxides. Here, tetrafluorobenzonitrile was deprotonated by lithium terzbutoxide and then aminated with a benzoylated hydroxylamine and a copper catalyst. In this example, a polyhalobenzene was deprotonated with LDA at low temperature and then coupled with a diazonium salt. Diazonium salts react with phenols even without a strong basis, and many azo dyes are prepared this way on an industrial scale. Azo compounds can be reduced to hydrazines or to anilines. Here, iron in acetic acid brought about a clean reduction to the aniline. With propyl mercaptane, however, no reduction but only aromatic substitution occurred. Occasionally, metallated arenes can react directly with amines to yield arylamines without any oxidant. Often it is oxygen which regenerates the catalyst. In this example, a benzamide was metallated with copper acetate by chelate formation and then aminated with morpholine. The same benzamide as in the previous example could also be aminated with ammonia. Here, 2 equivalents of nickel chloride and silver trifluoroacetate were required, though. Strong heating of DMF can cause its decomposition, and in this example, an oxal anilide was aminated with dimethylamine by heating with DMF and an excess of copper triflate under oxygen. Like in the previous example, this reaction generated way too much problematic waste and is unlikely to become relevant for practical synthetic purposes. Iridium can form chelate complexes with aryl ketones, and with acids these can yield aminoaryl ketones. Here such a reaction gave an aniline protected as trichloroethyl carbamate. Also aryl palladium complexes can react with benzoylated hydroxylamines to yield arylamines. This here is a rather special case of a norbornene-mediated cyanation and amination of an aryl iodide, but aryl palladium intermediates generated differently may also be aminated this way. Let's check some nucleophilic aminations. In this older organic synthesis procedure, 1-nitronephthalene was converted into 4-amino-1-nitronephthalene just by treatment with hydroxylamine hydrochloride. Naphthalenes are, however, exceptionally reactive, and these conditions are probably not directly applicable to simple nitrobenzenes. Treatment of 1,3-dinitrobenzene with a large excess of isopropylamine and potassium permanganate gave a substantial yield of arylamine, as shown here. The problem of these reactions is that the amine also reacts directly with permanganate, and the yields may vary strongly depending on the reactivity of the amine. In this example, aniline was first lithiated at low temperature and then treated with 1,3-dinitrobenzene. Because no oxidant other than the dinitrobenzene was present, only a low yield of arylated aniline resulted. A better yield was obtained here. Lithiated aniline was added to 4-fluoronitrobenzene at -120 degrees Celsius, and after 10 minutes the addition product was oxidized with permanganate. Interestingly, no substitution of fluoride but only of hydride occurred. The addition of nucleophiles to unsubstituted aromatic positions is often much faster than that to substituted positions, and in this case the initially formed intermediate was trapped by oxidation before substitution of fluoride could occur. This example is similar to the previous one. Instead of chloride, hydride was substituted when lithiated 4-chloroaniline reacted with 2-chloro-4-nitropyridine. The excess nitropyridine apparently acted as oxidant, and a high yield of product was obtained after only 10 minutes at room temperature. In this example, pyrrole was arylated with nitrobenzene by treatment with an excess of sodium hydroxide in DMSO. The oxidant was oxygen, and only one isomer was obtained in high yield. Unfortunately, DMSO is a dangerous solvent, and heating DMSO with a strong bases or acids can cause a violent exothermic decomposition of this solvent. Thus, scale-up of this procedure would probably require a different solvent, for instance DMA. Related to electrophilic aminations are oxidative acidations, as the one shown here. Copper catalysis was required, and radicals were probably formed as intermediates. This here is a rather exotic strategy for the orthoamination of anilines. The aniline had to be converted first into a sulfamate and then treated with an activated hydroxylamine. Hydrolysis then yielded the unprotected diaminobenzene. Now some potential side reactions. Halogenated amines or amides can also act as halogenating instead of aminating agents. Here, for instance, 2-chloroanisole was chlorinated in high yield by treatment with a slight excess of N-chloromorpholine and sulfuric acid. Then, halogenated anilines sometimes isomerize, as in this example. The electrophilic halogenation of anilines and phenols in positions 2 and 4 is essentially reversible. Traces of bromide or hydrogen bromide can regenerate bromine from 2-bromoaniline and lead to the formation of other isomers and dibrominated or halogen-free products. Arylamines readily oligomerize in the presence of oxidants, as in this example. Thus, many of the examples I showed you required optimization and a careful selection of the oxidant to prevent destruction of the product. Here are some further references which I've also pasted into the description of this video. The next and last video of this playlist is about the electrophilic nitration of arenes. This is the most relevant carbon-nitrogen bond-forming strategy for unsubstituted arenes, suitable both for electron-rich and electron-deficient arenes. So don't miss it.